In this video, I want to compare some of the differences between an old standing pilot gas furnace and a more modern direct ignition gas furnace. This furnace is a standing pilot, so the pilot light's burning all the time. So that pilot light's burning using a whole lot of gas, whether you're using this system or not. This system with the standing pilot was used up to about 1991, maybe 1992, before regulations changed and they said, hey, you can't put these in anymore. So even if you had the very last model that was made, it's still going to be significantly old. And we're also going to talk about some of the safety aspects of that. Now, if you're talking to your customers, I don't want you going out there saying, hey, you need a new furnace just because it's old. What I want you to be thinking about is the efficiency of that furnace and also the safety factors of that furnace. This furnace right here, this particular model, is a 1980 model furnace, so it's pretty old in its age. This furnace is a 60% AFUE furnace. Now, those words, that abbreviation stands for Annual Fuel Utilization Efficiency. So what that really means is this furnace, of the natural gas that I'm buying, it's converting 60% of that natural gas in the heat that's going in to heat your house. 40% of that gas is just going out the flue pipe. So you're losing 40% of that just straight outside. This furnace, the direct ignition furnace, this furnace is about 80% AFUE, annual fuel utilization efficiency. This furnace, of the natural gas that I'm bringing into this furnace, it's converting 80% of that into heat, heating the house. 20% of that's going out the flue pipe. It also has an advantage of many more safety features, as well as it doesn't have that pilot light that's burning in there all the time. So as we break down some of the differences between this, the size of this furnace is going to make a big part of that. They rate furnaces by the input BTUs, so taking the gas, converting it to input. So this furnace had an input of 80,000 BTUs, and this had an input a slightly smaller at 75,000 BTUs. There's only a 5,000 BTU difference, but let's go into a little bit more detail. This furnace is 80,000 BTUs input. It's only using 60% of that to heat the house. So the actual heating content of this furnace is 48,000 BTUs. Since this furnace is a 80% furnace, we're actually getting 60,000 BTUs of heat. This furnace right here is actually larger as far as the amount of heat we're getting into the house than this old furnace. So when you're sizing furnaces, the efficiency of that furnace is going to play a part. If I put an 80,000 BTU furnace and replace it with a new 80,000 BTU furnace, it would be too large for the house. And oversizing a gas furnace is one of the worst things you can do. It's horrible being able to control humidity. Your customers are never going to be happy. So you've got to take into account the efficiency of that furnace when you're changing it. In this case, this furnace, 60,000 BTU, is going to be significantly larger than this old furnace that was there. So let's continue on with this. Let's talk about some of the efficiency of these furnaces. Both of these furnaces would be installed typically inside of a closet. So if it's inside a closet, since they're both upflow, meaning the blower's down here, it's taking air from below, moving it through the heat exchanger into the ductwork above. Same here, taking the airflow upflow through above. There'd most likely be an evaporator coil here as well as an evaporator coil here, but it's an upflow furnace. If this was installed in a closet, the air in that closet has to be separate from the air of the house. So the closet would have what you call upper and lower combustion air. There would be a pipe coming from the closet, from the attic, say about halfway, and another one coming, actually so many inches from the top, and another one coming within so many inches of the bottom. That air coming into the closet is what's going to be burnt right here in this furnace. It's very important that it stays separate. This furnace has the same thing. Depending on the size of the furnace, the size of the hole, so many inches from the top, so many inches from the bottom of the platform, is the air of this closet for this to burn. The air from the house has to be sealed off. So this furnace would have to be sealed on the bottom so it's not mixing the combustion air, the air it needs to burn, with the air of the house. Now these upflow furnaces were also installed in basements. So if you were to install this furnace in a basement, there would be a hole cut in the side like this, and you would have your filter system here, and your ductwork would come down, the return air goes into the system, you heat the air up, the supply air goes back into the house. Same with this system, the hole would be on the side, your filter would be here, the return air comes into the furnace, you heat the air up, the warmer air goes back into the house. So as far as what they're doing, they're taking fuel, they're burning that, and that's why we're getting reheat. Lots of little differences about how that system works. First thing we're going to talk about is these doors. Both of the doors in the upper section have these holes in it. This is for the air for it to burn, like we mentioned. So what we're going to do is we're going to pop these doors off, and we can get into the guts of this system. And this older furnace, a little ornery today, but we'll put that door down there, and we'll pop this door here. Now another thing I want to mention is if you're working with your customers in different units, you want to practice putting different doors on. You want to know how that door works. You can learn all this technical jargon. You can learn all about how these system works. You can know all these. But if you're trying to put a door on and you have time in front of the customer, it makes you look bad. So make sure you know how to put these doors on, because it's really embarrassing when the customer goes and puts the door on for you. So now we can get to all of our gas components, our gas valves, our burners. But next thing we have down here below is the blower doors. And if we notice, these doors are louvered. They allow air to go in. But where the blower is a solid door. That's very important, because when this blower is running, it's pulling air from the house. And again, I can't stress this enough, it's not mixing it with the combustion air. So as I pull this door off, and then notice it's going to be a little tighter. There we go. Now we can get to our blower, and the same thing on this door here. We're going to pop it off, and now we can get to our blower. So both of these systems have a door interlock or a door safety switch. This one is here and this one is here. That's a very important aspect, because when this door comes off, it shuts the power off to the furnace, so it will not run. Why that's important is because some customers will take this door off to get to the filter. So if they don't understand how the doors work and they try to put the wrong door back on, it won't let the switch push in. This keeps them safe, so it's not pulling combustion air into the unit. That's really important for you to understand, because as a technician, you'll see a lot of people want to tape these switches to leave that on so they can check the whole system while it's working temporarily. The problem is, I've seen over and over again, people forget to take that tape back off, and that causes a safety hazard. Now the door may fall off, not get on there correctly. Now the blower is pulling the combustion air from the burner section into the house, and that could cause a carbon monoxide poisoning effect, and we don't want that to happen. What I use is a magnet glued to a 90-degree L. That way I cannot put the door back on without taking that magnet off, and that's a tool, and I don't ever want to leave a tool behind. So there's many out there that's already pre-made. You can make your own, but some kind of a magnet system that holds that switch in on these different furnaces, so you don't have to worry about taping it. Please, it's a bad habit to tape it, just because if you forget, that could be a liability issue. On this old furnace, we have this little wire mesh and this old filter that you would slide out. So the customer had to take this door off, both doors off, to change the filter all the time. So it was a huge issue with that door not being put on correctly, or them leaving the door off so that they wouldn't have to go through all that mess. And it's been, people have been sick and died from that. On this furnace, it's a little bit more modern, because in addition, somebody has added an external filter base. These filter bases are great because you can open this and slide the filter in and out without taking the door off. So I've never installed a furnace without installing one of these external filter bases, because it's so much easier for that customer. It's hard enough getting your customer to change filters anyways. It's going to be so much harder to get them to change filters if they got to worry about going through a whole lot of hassle. So this way they can lift this door up, slide the filter out, slide a new filter in, and they're not messing with anything with the system. And remember, a good filter is going to be the key to that system lasting a long time. Now if this was a basement unit, this same filter base would be mounted on the side here. And there's tons of different brands and styles and types and efficiencies and pressure drops for these filter bases. That's a whole nother topic, but it's a really nice accessory that every furnace should have. So now that we can see the components of this, we have our blower, we have all of our controls in here. Now if we see, it's still the basic same thing. We're trying to burn gas, mix it with air, the correct amount, and draft it out. This one though is significantly different at how it's done. The standing pilot's going to burn all the time. When a thermostat calls for heat, it just energizes this combination gas valve. We come through across that pilot, ignites into a flame, burning in that heat exchanger. The pilot lights notoriously were being blown out, and you had this one safety called a thermocouple. A thermocouple would burn, would be right next to the pilot. The pilot would burn against it, and you would, that's its only real safety feature. If the flame blew out, the thermocouple would cool off and keep this combination gas valve from working. But sometimes you have an issue to where the flame would be blowout, the thermocouple would keep this valve open too long and gas would build up, and then when it finally ignited from a spark, it would become a miniature little explosion. So that was an issue. Also, there was no safety to keep that gas from rolling back out. This furnace has flame rollout switches. They're extra safety devices. So if the flame was to come out of this heat exchanger, this shuts the whole system down quickly and efficiently. This has none of that systems. Let's also talk about the draft. As this furnace burns, it just naturally drafts up It collects at the top of the heat exchanger and it just naturally drafts out the flue pipe. I can literally stick my hand up inside of this flue pipe and that's all there is. So a windy day is going to blow that combustion gas back into this closet. It could seep back through any little cracks into the house. It was a very simple design, but there was no safety aspects. With the new furnaces, what we have is this inducer fan motor. This control board energizes this fan motor first, and this is pulling a draft through the heat exchanger, so it clears out the heat exchanger as well as starts the draft to the flue pipe. So this way, if you have a windy day and it's pushing air back down, it's not going to be dumping those combustion gases out into this closet. So this motor right there makes it more efficient. And these older systems, what we had was our burners had an air fuel adjustment. So we had to actually adjust, open and close this opening so that we could adjust how much air is coming in to set the flame. You're supposed to use a combustion analyzer, but a lot of people just do it by looks, but we had to adjust the air fuel mixture so this would burn correctly inside that furnace. The new ones are quite simple. The new ones use these in-shot burners, and as we shoot the gas in, it mixes with primary air on the sides, and these burners are much smaller, mixes the air and the fuel, directs the flame, but it's a nice small one, and it's shooting the flame actually sideways. This makes it nice and simple, but you think, how is it mixing the air and the fuel? And the engineers have done a significant amount of work for us. What they've done is they've put this inducer motor that we talked about. They've designed this motor so they know exactly how much air it moves. And by having a precise hole right here, this will move an exact amount of air. Now, if we know exactly how much air is being moved, and they know exactly how much gas is in here, there's no need to adjust the air. However, it is important to make sure the gas pressure is set correctly. If you want to know the correct way to set the gas pressure, RTFM. Read the fabulous manual. So every system's a little different as far as altitude or changing spuds and orifices, but most gas valves you'll see it says 3.5 inches of water column. So there's different settings that you set the gas pressure. Once you get the gas pressure set correctly, then the air side's already done for you. So they made it a lot simpler for you to work on. Now, the problem is if this fan motor stops working, it's going to be an issue because there's nothing keeping the flames pulled in. So they've also added this pressure switch. So this pressure switch is a pretty simple device. When this is pulling a vacuum through the heat exchanger, it pulls a vacuum to this pressure switch, or negative pressure switch as it's called sometimes. And this tells the control board, hey, this guy's working. So you have this as a safety feature, as well as you have a second safety feature here, as well as the flame rollouts. Now on this side, what told the blower to come on once it got warm enough was called a fan limit switch. It was a limit switch and a fan switch. So this was all you'd see on this side. It's actually right here. You won't be able to see it at this point, but it would sit between the heat exchangers, and when the heat exchangers got warm enough, the bimetal would turn, and when it got warm enough, it would bring the fan on. This one uses a preset timer. The engineers have decided exactly how much heat it takes to get heated up to the right point, how long that takes, and it brings the fan on. With this one, if it was to overheat or have too much heat in there, if it continued to turn, this would shut off the combination gas valve. On this system here, we have a limit switch up in the far right-hand corner. It's just a bimetal switch. If it gets too hot, it shuts the furnace off. So as far as it getting too hot, it shuts the furnace off. Now, while we're talking about the limit switches, if a primary limit switch fails, you need to be thinking first, airflow, airflow, airflow. A lot of students, when they get into class, they think, whoa, the primary limit, it's getting too hot, and they think the gas side. But you need to be thinking the airflow side. The gas is going to be already set for us. So if that primary limit's failing, what's happening on the airflow? Is that filter dirty? Is this blower in the right speed? Is it moving enough air? Is the evaporator coil above it cleaning, or is it dirty, restricting airflow? Is there too many vents closed? Anything with airflow, you're not moving enough air across that heat exchanger to keep it cool, so to speak. So limit switch trips on any system, you need to be thinking airflow, airflow, airflow. So very simple process, whereas this one has the control board monitoring every single aspect of the system. Now let's talk about safety after it fires up. This system has a flame sensor, which is a single rod that's going to be in front of the burners. That single rod is what's going to sense a flame. And it looks just something like this. We'll get into the details of how this works in another video, but it's just a single rod flame sensor. And it's actually on the opposite side of where it ignites. So this particular model is a direct spark ignition, DSI. So it arcs, makes an arc, and it lights the gas, and then it has to go all the way across all the flames before it senses a flame on the opposite side. These old furnaces didn't have anything like that. The only thing that they had was their standing pilot light. Sometimes you would see on these furnaces, this one would light right here, but the other one wouldn't light. And when it would finally light, all the gas would build up, and you'd have a flame roll out of the system. So I always tell my students, on any gas furnace, whether it's a modern one or an older one, you want to make sure you're standing to the side of that furnace. In case that flame rolls out, it's not going to hit you in the face. There's been technicians before that lost their mustache, messed up their beards because they were standing right in front of that furnace. So you stand to the side, so if that flame does come out, it's not going to hit you. Once it lights up, you can then look in there and see everything's, make sure everything's working correctly. So this one has the protections for that, this one doesn't. This one over here is that pilot light burns all the time, and this one is going to have that spark igniter, so it's going to spark and ignite the main flames directly, immediately. Now, some companies also use a hot surface igniter called an HSI, hot surface igniter. These are also very popular. It sends 120 volts to them. This gets extremely hot, and then as the gas comes across this igniter, it ignites into a flame, burning the heat exchanger. So, very efficient. A lot safer, this new model. But let's talk about the heat exchanger. I've said heat exchanger several times. We haven't looked at it. So let's take a look at that now. So we're going to turn this older unit around. And we can see the heat exchanger for this big metal component here. And we're going to turn this guy around. And we'll look at its heat exchanger. And we'll see that it's a whole lot smaller. So we're going to compare both of these heat exchangers. And the very bottom side of this one is where the burners are going to be, and the flame's going to be burning up about no more than about this high right here. So if we were to look at the burners, these are the burners that we would have. They would be sitting inside of this heat exchanger, and the burners would be sitting here burning up. Now, once the flame stopped about here or so, the gases are still going to be extremely hot. So those gases are heating up the metal from the inside, and this is exchanging the heat from the flames and the hot gases to the air on the opposite side. So the air from the house is blowing over the outside of this, and inside this tank or this chamber or this heat exchanger is where the flames are going to be burning. So this is going to keep the flames and the gases separate from the air in the house. So this would be the combustion side, but this whole entire thing is the heat exchanger side. On this we have a very similar situation, except this side here is going to be where flames burn. This is going to be our combustion chamber. If we saw that these little burners are going to be on the other side, it actually shoots the flame inside of this heat exchanger. The flame burns no more than this far here, then it collects together. Those gases are still very warm, so the gases continue to run back and forth through the secondary tubing, and that collects in a box here that goes to our inducer fan that's pulling that draft out. So a whole lot smaller space, and we can transfer more heat versus this big long system here. The system here notoriously would rust out. You can see these very dark rust spots. The evaporator coil is most likely leaking, and these would rust out all the time. Plus, where that pilot light would be burning, it would be below dew point in several situations, especially in the summer, and it would cause these heat exchangers to rust out. Anywhere there was a seam, anywhere these little bends were common points for these to crack. Now, when this heat exchanger cracked, it would allow the combustion gases, the carbon monoxide, all these other fumes to come out of the heat exchanger into the blower stream and actually poison the customer in their house. So these heat exchangers leaking was a huge issue, and we were always checking them. Many ways of checking them. We would send a light inside, a camera, mirrors. There's many methods of checking these, but these old things would crack and leak carbon monoxide, and it was a huge, huge safety issue. Now, this heat exchanger has a special coating on it. Usually it's a type of galvanized. They even made some that were stainless steel, but even the other ones, they didn't rust out nearly as bad because the flame wasn't actually touching against this metal. The flame was directed to shoot inside this tube, and because this inducer fan is pulling a draft through this heat exchanger, the flame was just brush against the side, so it didn't burn out. Now, you would see sometimes people wouldn't set the gas pressure correctly, and it would cause these tubes to burn out. That's definitely going to be an issue. If your evaporator coil is leaking water on here, it's definitely going to rust out. It's still going to be an issue. But if you had a hole in this heat exchanger, it's less likely, still possible, but less likely to immediately poison the customer. Because if you have a hole in this heat exchanger, this whole heat exchanger is negative pressure. This fan is pulling a draft through this heat exchanger, so it's negative pressure. The idea is if you get a small hole in here, the heat from the air from the house would actually go into the heat exchanger, to whereas this one, the hole in the heat exchanger would be pulling gases out into the house. So, still an issue. You should never run a unit with a cracked heat exchanger or a hole in it under any conditions. It's just a little safer, the fact that if you did have a hole in it, it's not going to be an immediate death situation. And I don't like a death situation whether it's immediate or long. So this heat exchanger, a whole lot smaller, a whole lot more efficient. There's tons of different styles of these, but it still works the same. They're shooting the flame horizontally across this. I'm going to turn this one a little bit more so you can see between these two heat exchanger tubes. This one had only 2 burners, so we had the 2 heat exchanger tubes. They had 5 or 6 burners long, depending on the size of the house or the BTUs that it needed. So this one only had 2 burners, so it has 2 separate heat exchangers. Between these 2 heat exchangers, if I was reaching my hand in here, I could feel this fan limit switch. So this side of the fan limit switch is between this heat exchanger, like so. The control side that you see is on the opposite side of that heat exchanger. So this is where the air from the house goes and the flames burn inside of here. So this heat exchanger was one of the big points we're always looking for. Hey, are these leaking? Are they safe? Those are always some pretty important issues we look at. On this heat exchanger, can still leak. It's still going to be an issue, something we're going to look at, but it's much easier to make sure to keep the customer safe and more efficient. All right, so we've talked about a lot of important parts of this heat exchanger and the furnace itself. We'll turn this back around and we can see the front. This heat exchanger here, all the way up to this furnace, all the way up to 1991, 92, this is an 80 model. We talked about how much more efficient this system is, an 80% furnace, but both of these furnaces, they're still category 1 furnaces. It's still a natural draft flue pipe. The flue pipe in both of them are going to be very similar, as fact as the hot gas needs to be a certain temperature so that it drafts out. This is a non-condensing furnace, so that means if we get too much heat out of this flue pipe, then it will start to condensate. So a category 1 furnace is going to be a natural draft non-venting. Just because it has this inducer fan motor doesn't mean that this is positive pressure. This is still negative pressure. It's natural drafting up. So keep that in mind. This fan motor's job is to pull a draft through the heat exchanger and induce or start a draft, but its job is not pushing. It's not pressurized on the side. I've seen people want to put the flue pipe going horizontally because they think that it's pushing air, and that's not true. So you need to keep that in mind. Anytime you're changing any furnace, you always want to check the flue pipe to make sure there's no cracks, make sure that there's no corrosion or water damage inside of that flue pipe. Going on differences of these furnaces, we know that if you see one, it's from a 1991 model standing pilot furnace. It's going to be a safety issue and an efficiency issue. You really need to be talking to that customer about a new system for all those reasons we talked about, not just because it's old. If you see this furnace here, it is much safer. It's got a whole lot more safety components. But this furnace right here was manufactured in 1999. So this furnace is 21 years old as of today. But still, I wouldn't have an issue keeping this furnace running. Well, maybe not since I cut a bunch of holes in it. But if this furnace was fully operational, I wouldn't have any issues. As long as there's no holes in the heat exchanger, it's still a very safe furnace. The new furnaces now for the Northeast are required to be 90+% efficiency, condensing furnaces. We'll get one of those in a separate video and break that down. This furnace is still available all through the South and the Southwest. The temperatures don't get as low. You don't use the heating side, so they don't have as stringent of restrictions on those. But that's the difference between your 2 gas furnaces. If a customer's watching this, you got a standing pilot, it's time to upgrade, it's time to change it. But as technicians, we need to know everything we can about these furnaces. If you're a younger technician in the field and you haven't worked on these and you come across one, it's best to call a senior technician out there. Get some advice. There's a lot of little tricks to these systems that we haven't talked about. You don't want to get yourself in the middle of a liability issue. Also in that, we're going to be breaking these furnaces down completely entirely, so you see all the components of how they work. Not that I recommend you work on these old furnaces, but the more that you know, the more that you understand, the safer you can be, the more knowledge base. And we're also going to do the same thing with this guy. We're going to break it completely down so we understand how it works and why it works. Have a great day and keep learning.